So now let's start today's first lecture from Yutao Liu. Yutao Liu is from University of Chicago, and he will talk about complex orientations, formal group laws, and example of KU. You lost your sound again.
Yeah, so I know the microphone is not working at all. Anyway.
Okay, now it's perfect.
Right. So thanks for inviting me to the conference. Today I will talk about complex orientations on general cohomology theories and the formal groups, which arise naturally when you further analyze the structure on the complex oriented cohomology theories. So the initial idea of the orientation comes from vector spaces, which corresponds to your choice of basis elements. This idea can be further extended to manifolds, which is the first kind of orientation we are going to talk about today. So here we have two different manifolds, as you can see. We have a torus and we have a Klein bottle, which is a twisted version of the torus. Intuitively, you can say that the torus is orientable, but the Klein bottle is not. So to make this idea to be more precise, because you can easily distinguish the outside and inside of the torus, but you can never do that for the Klein bottle. In fact, the Klein bottle cannot be embedded in the three-dimensional space. So to make this idea more precise, if you consider any point on the torus, for any point on the torus, I should be able to draw. 1 second. If you consider any point on the torus, then the local orientation at this point is basically the orientation of a small neighborhood object, which is homeomorphic to an n-dimensional disk if your manifold has dimension n. In our examples, such kind of local orientation can be expressed by a choice of the normal vectors. You can either choose it to pointing upward or pointing downward, which will correspond to the two orientations on this small disk. You can do the same thing on the Klein bottle. Although the Klein bottle itself is not orientable, you can still do it locally. Now the problem is, if you want to make a orientation on the whole manifold, then what you want is you want a continuous choice of normal vectors. You can easily do this for the torus because you can choose all the normal vectors to pointing outside or pointing inside. But for the Klein bottle, for example, if you begin at this point, and if you go along this path, something like this, okay, then basically the normal vector here, it will be changed gradually. Sorry for my bad drawing. To the normal vector pointing inside. In other words, you can never make a continuous choice of normal vectors on the Klein bottle. To be more precise, you cannot make a continuous choice of local orientations. In algebraic topology, we can express the local orientation by something we call the local homology. If you begin with an n-dimensional closed manifold, and for any point on the manifold, the normal vectors at the given point, I mean, the two choices of the directions of the normal vector corresponds to the two generators of the local homology, because M is a manifold, so the local homology is always the same as the n homology of the n-dimensional speed. So now, if you want to choose an orientation on the whole manifold, one natural idea is you only need to choose an element on the global, on the global homology, which is the homology of the whole manifold, such that its restriction on each local homology gives you the choice of the normal vector at that point. So here we have the first definition of the orientation on manifolds. If you begin with a dimension n manifold, basically it is an element in the degree n homology of M, which will be sent to a generator on all the local homology groups. You can do this easily for the torus because you know H2 of the torus is Z. 1 second. However, you cannot do it for the Klein bottle because its H2 is 0. Some small computations on homology. So the same idea, in order to define a global orientation, basically you want a continuous choice of local orientations. Here is how we define it on the manifold. We can also do the same thing on the vector bundles. So if you begin with a vector bundle with dimension n, which means over each point of M, you will have an n-dimensional vector space. So you can consider the orientation on that space. And now you want to make another continuous choice to cover the whole vector bundle. Similarly, you can use the local homology to express such idea. If you consider Vx as the vector space, I guess there's a typo here, a vector space over the point, then the local orientation on this vector space is expressed similarly as the local homology of the given point. Now the problem is how to make a global choice. One idea to think about this is you can use the construction of the Thom space. Because the local homology agrees with the homology of with the reduced homology of the Thom space at the given point. If you consider this small vector bundle, which is one single vector space over one single point, then the local homology here is the same as the reduced homology of the Thom space. Moreover, you have a global object because there's a natural inclusion from the Thom space of each local bundle to the global bundle here. So one idea to define the orientation on vector bundles is to choose an element in the global Thom space. But here, because we want an arrow to go the other direction, so now we use cohomology. So we define the orientation on the vector bundle to be an element in the n-dimensional. So if you assume the vector bundle has dimension n, it is an element in the degree n cohomology of the Thom space, which is sent to a generator by the induced map onto any local Thom space, which gives us a local orientation. We also call such element to be a Thom class. And each time when we have a Thom class, we will have the famous Thom isomorphism. So the rough idea is, if you consider the cup product with the chosen Thom class, you will have an isomorphism between the cohomology of the base space to the reduced cohomology with degree shifted by n of the Thom space. So in conclusion, if you want to define an orientation on vector bundles, basically you want to choose an element in the Thom class, which express such, in the cohomology of the Thom space, or which is called the Thom class, which express such orientation. So we can make this idea to be more general. Basically, here we use the ordinary cohomology to obtain our expression elements. But in general, we can replace this ordinary cohomology by any general cohomology theory. So if you have any arbitrary commutative ring spectrum on E, because we will require some cup product. So let's assume you have a product on E. Then you can define something we call the E orientation. It's the same as the orientation. It is the same as the traditional orientation. Basically, you just replace all the cohomology theory by the E cohomology theory. With such definition, you can define something called an E orientation. The classical orientation on the vector bundle is the same as the HZ orientation because we use the ordinary cohomology theory as the detecting theory. In fact, you can relate the orientation on the manifold and the orientation on the vector bundle. Basically, the orientation on a manifold is the same as the orientation on its normal vector bundle. So you can use a combination of the Thom isomorphism and the Poincare duality to relate the two choices of the orientation. One in the homology of the manifold and the other one in the cohomology of the Thom space. Oh, 1 second. So if we go back to the examples of the torus and the Klein bottle, basically you can see that both the torus is both Z orientable, actually HZ orientable, and also HZ/2 orientable. For the Klein bottle, it's not HZ orientable because its degree 2 homology with Z coefficient is trivial, but it is still Z/2 orientable. Because when you choose Z/2 as the detecting theory, basically you are not distinguish the normal vector pointing outside or inside. You are going to view these two things as the same normal vector. Moreover, the degree 2 homology of the Klein bottle with coefficient in Z/2 is the same as the torus, which is Z/2. So you can still choose an element here, which is sent to the generator of all the local homologies. In fact, if you consider all the closed connected real manifolds, so they will always be Z2 oriented. So this motivates the idea to say the cohomology theory. The cohomology theory with coefficient Z/2 itself is orientable instead of saying any single manifold or any single vector bundle is orientable. So this gives us the initial idea to define an orientation on a general cohomology theory. So from now on, we will consider everything to be complex. We will consider all the vector bundles to be complex vector bundles because the real case is easier than the complex case. So the rough idea is, if you want to say a cohomology theory represented by the spectrum E is complex orientable, then basically you want to say all the complex vector bundles are E orientable. And also you want to make a universal choice of the E orientations on all different complex vector bundles. So here you have the definition which concludes these two ideas and makes them more precise. So you know that for each single complex vector bundle, its orientation is expressed by an element in the Thom space, in the cohomology of the Thom space. So basically now you want to choose one Thom class for each complex vector bundle. And also you want this Thom class to be mapped to a generator for each local Thom space, for each local orientation. So 1 here is the definition of the E orientation before. 2 and 3 are the compatibility relations, which explains what you mean by requiring a universal choice of E orientation. Basically, you want the choice of the Thom class to commute with the product of vector bundles, and also you want to transfer the direct sum of vector bundles to be the product of the corresponding cohomology classes. So in fact, in practice, when you want to define a complex orientation on some cohomology theory, you don't have to choose a Thom class on all the complex vector bundles. You only need to consider a special type of complex bundles, which are called topological bonds. So I'm going to show you the definition. So you consider the complex projective space with dimension n. You can view Cpn here as the collection of complex lines in Cn+1. Then you can define the topological bundle, which we denoted by On. So it is the collection of, so basically you want to assign the line. So for each point in Cpn, you want to assign the line it represents as the line bundle, as the line bundle over this point. So here you have a topological bundle. If you consider the projection onto the first generator, basically you want to project the whole line into the representing element in Cpn. Then you have the complex line bundle. So the idea here is, if you want to get a complex orientation on a cohomology theory, basically you only need to find a nice choice of the complex orientation on all the tautological bonds. Moreover, you can further simplify such kind of choice from the cohomology of the direct limit of this complex projective space. So there are some observations of those tautological bundles. So first, the Tom space of the On here is the same as Cpn plus 1. Moreover, if you consider the natural inclusion, so among the different complex projective spaces, so they will imply inclusions of the tautological bundles, which will further agree with the inclusion of the same complex projective spaces with degree shifted by 1. So if you apply the E-Tom classes, if you apply the E cohomology on this sequence, so recall that for each On here, the complex orientation on On is a Tom class. So let's use Cn to denote that. And similarly, you have another Tom class, Cn minus 1, and so on. So because the choice of the Tom class commutes with the products of vector bundles, and also On is the pullback of On plus 1 through the inclusion from Cpn to Cpn plus 1. So if you consider this sequence, then the chosen Tom class here will be mapped into the Tom class here. So you will have a sequence of the Tom classes, which will be finally mapped into a generator inside a pi not E. And moreover, because you know the Tom class agrees with the complex projective space with degree shifted by 1, so now you have such sequence. So you have a sequence of classes chosen, and also a sequence of E cohomology. Now, if you take the limit when n tends to infinity, you will obtain an element in the E cohomology of Cp infinity, which is the inverse limit of this sequence of elements. And this element in the cohomology of Cp infinity will be sent to a generator of E square of Cp1, which is the same as pi not E, because Cp1 is the same as S squared, the two-dimensional speed. So in conclusion, if you have a complex orientation on a spectrum E, then basically you can obtain a special element in the E cohomology of Cp infinity, which is mapped to a generator in the E cohomology of Cp1 as a module over pi naught E. So the other direction is also true. If you begin with a complex orientation, you can find such special element. On the other hand, if you can find such special element, then you can always extend it into a complex orientation of E. In other words, the complex orientation of E is the collection of the Tom class over all the complex vector bundles. But you only need to make your choice over those tautological vector bundles, which is further expressed by a special element in the E cohomology of Cp infinity. And here are some examples. So if you begin with the ordinary cohomology Hz, so we are going to use 2 here as an alternative definition of the complex orientation because it's easier to deal with. For the ordinary cohomology Hz, so by a direct computation on the ordinary cohomology, the cohomology of Cp infinity on degree 2 is the same as the cohomology of Cp1. So you only need to choose one of the 2 elements in HP of Cp infinity, which is mapped to a generator in HP of Cp1. In other words, Hz is complex orientable, and you have 2 choices of the complex orientations. A slightly more complicated example is the complex K-series Ku. So recall that KU is the cohomology theory, which consists of the, which is the Grothendieck group of isomorphism classes of complex vector bundles. So this one is the Grothendieck group of all the isomorphism classes of complex bundles over the space X. And we have the Bott periodicity, which explains the structure on the KU cohomology. And also there's another computation by Bott, which computes the KU0 cohomology of CP1, which is the same as S2. So this one is so as a Z module, it is generated by the trivial bundle 1, and also the tautological bundle over CP1 minus 1. So this one, the square of this one is 0. So now when you consider the reduced KU cohomology, you want to remove the trivial bundle. So a natural choice of its generator. A natural choice of the generator of the reduced KU cohomology of CP1 is represented by the tautological bundle minus the trivial bundle. So now, in order to find a complex orientation on KU, basically you want to find an element in the KU cohomology of CP infinity, whose restriction is this tautological bundle minus 1. So what you can do is you can just choose it to be the tautological bundle over CP infinity, which we denote by O infinity minus 1. Then if you consider the inclusion from CP1 to CP infinity, the restriction of this element will be O1 minus 1. In other words, it's a valid choice which satisfies the condition 2. So the KU cohomology of CP1 is generated by this special element, and here we choose one element in KU cohomology of CP infinity whose restriction agrees with this special element. In other words, we actually define a complex orientation on the complex K-series KU. So this one is the most canonical choice. Clearly, there can be other choices which has the same the same restriction. Maybe I should stop first and ask if there are any questions. I guess I'm going too fast, maybe.
There is one question in the chat.
Oh, really? Who proved this theorem? You mean this theorem? This one, right? So I can't quite remember who proves that, but actually the idea, I already told you how to go from 1 to 2. The idea from 2 to 1 is you can view CP1 as MU1. So MU1, you can view that as the kind of generating part of the complex cobordism spectrum MU. And then in the next talk by Zhipeng, you will know that MU is a universal example among all the complex oriented cohomology theory. In other words, if you CP infinity, so not CP1. In other words, if you have a special element in the E cohomology of CP infinity, so this will further implies a map from the universal example MU back to E, which will further gives E a complete complex orientation. Yeah, so you will know more information about this spectrum in the next talk. Okay. So here is another point of view about the complex orientation. So recall that one way to define the complex orientation is a special element in the E cohomology of CP infinity, which restrict to a generator of the E cohomology to the E cohomology of CP1. You can view this restriction as an extending problem. This one is the same as extending a map from CP1 to E with degree shifted by 2 to a map from CP infinity to E. And you know, CP infinity is the direct limit of all the CPN. So this extension is the same by extending the map from CP1. So by degree plus 1 each step to CP2, CP3, and so on. If you want to extend the map from CP1 to E to CP infinity to E. So this one is the same as you want to make the extension one step at a time. You want to climb up from CP2, CP3, and so on. If you just consider CP1 and CP2, basically CP2 is CP1 plus 1 additional 4 cell. So you will have a cofiber sequence between CP1, CP2, and S3, which is the location of the 4 cell over CP1. So if you apply the cohomology, if you apply the E cohomology, you will have the following long exact sequence. So now if you begin with an element here, and you want to extend it to an element here, you will always have such an extension if pi 5 of E is 0. Because if pi 5 of E is 0, then this map will be surjective. So you can always find a per image of the corresponding element here inside the E cohomology of CP2. In other words, you can say the obstruction of the extension inside the fifth homotopy group of E. And you can apply the same argument to the higher extension. So the obstruction of extending a map from CPn to a map from CPn plus 1 is contained in pi 2n plus 3 of E. In other words, if pi 2n plus 3 of E is 0, then you can always extend such a map. So now if you want to extend a map from CP1 to all the CPn and finally take the limit to CP infinity, basically you have the obstruction on the nth degree homotopy groups of E. In other words, if your spectrum E happens to have trivial order degree homotopy groups, then you can always find a complex orientation on them, because you can always extend an element from the E cohomology of CP1 to an element of the E cohomology of CP infinity. So here is another way for you to determine whether a spectrum is complex oriented. Examples includes our previous two examples, HZ and KU, because the homotopy for the first one is Z, which is concentrated in degree 0, while the homotopy of the second one is the periodic graded group, which only concentrates in even degrees. Actually, the examples also includes the complex cobordism spectrum MU. So this one is slightly more complicated, but actually all its generators still only appears on even degrees. So all these three spectrum only has trivial order degree homotopy groups, which means all of them are complex oriented. But of course, if you want to find a concrete complex orientation, then you have to further study the cohomology series expressed by those spectra. So now we have finished the idea of the complex orientation on general cohomology series. So now I want to talk about the formal groups. So you know the complex orientation over the cohomology series E can be expressed by a special element in the E cohomology of CP infinity. If you further study the structure of this special E cohomology, you will have something which is called a formal group. So first, I'm going to give you the definition of the formal group. In fact, a formal group law, to be more precise. If you begin with a ring R, then the formal group law over the ring is a power series. So Rxy, I guess it should be small x and y. So this one is the collection of all the infinite series, which is expressed by, let's say, Aij of x to the I, y to the j, with ij greater or equal to 0. So the formal group law is expressed by such power series, which satisfies the following three conditions. The first one is the commutativity. The second one is the the unit property. The third one is the associativity. In other words, if you use this one, so you can view this one as the group as a product, which makes the series over R with two variables into a group, which may be one reason why we call it to be a formal group. And if you have two different formal groups over the same ring, you can define maps between them, which is expressed by a power series with one variable, which commutes with the two formal groups F1 and F2. In other words, if you begin with the formal group F1 and then you apply F, you will obtain the formal group F2. And you can see in which case F can be an isomorphism. So it is an isomorphism if and only if it is invertible in the power series of R, which means the coefficient on X is an invertible element. And there are some typical examples about the formal groups. So we have the additive formal group, which is denoted by GA, which is the usual addition. And also we have the multiplicative formal group. This one is the same as the usual multiplication if you plus everything by 1. Basically, you will have 1 plus g of xy agree with 1 plus x times 1 plus 1. So these two special formal groups basically represents the usual addition and the multiplication. So if you come back to the complex orientable cohomology series, if you want to study the e-cohomology of CP infinity, you will have something which looks like a formal group. So the idea to compute the e-cohomology of CP infinity is the application of the Thiele-Herzenberg special sequence. If you haven't seen any special sequences before, you can just view this one as a machine in a black box. So the input of the machine consists of the ordinary cohomology of the space and also the homotopy of E. Then after you apply this machine, it will give you the output, which is the e-cohomology of the given space. However, this machine does not work in general. There will be some special requirements to make it computable. In our case, it works when E is complex orientable and also X is a finite CW complex. So what we want to compute is the e-cohomology of CP infinity. So in order to compute the e-cohomology of CP infinity, we can compute the e-cohomology on CPn first, and then take a limit. So if you import x equals CP to the n, then basically the e-cohomology of CPn will agree with will looks like a polynomial algebra over the homotopy of E, with one generator whose n plus 1's power is 0. So when you take n to tends to infinity, the e-cohomology of CP infinity will behave as the power series, the formal power series over the homotopy of E. And moreover, here you can choose the variable t, which has degree 2, to be the given complex orientation. The same argument can be applied to 2 copies of CP infinity, for which case you will have the formal power series with 2 variables, x and y. So the reason why we compute the e-cohomology of 2 copies of CP infinity is because there is a natural product we can define on CP infinity. So here the 2 variables x and y, you can choose them to be the image of the given complex orientation by the 2 projections. So we can define the natural product on CP infinity because we can view this one as BU1. which is the classifying space of the dimension 1 complex vector bundles. So recall that the way to define the product on K theory is to use the tensor product between vector bundles. So and here, because BU1 is the classifying space, so there will be a map from 2 copies of BU1 to 1 copy of it, which represents the tensor product between different complex line bundles. To be more precise, if you have 2 different line bundles over X, which are classified by 2 different maps, F1 and F2, then their tensor product will be classified by the composition. You map X from F1 to the first copy and F2 to the second copy, and then you apply the multiplication N. So this map is classifies another complex vector bundle which agrees with the tensor product of the 2 given bundles before. So if you apply the equal-homology of this natural product, you will have a map from the equal-homology of 1 copy of CP infinity to the equal-homology of 2 copies of CP infinity. In other words, you have a map from the power series with 1 variable to the power series with 2 variables. And here you can obtain a homo group if you consider the image of T. So you can define the image of T, which is the power series here, as the formal group. The reason why this gives you a formal group is it is defined by the tensor product between vector bundles. So you will have the commutativity and associativity naturally. Moreover, the tensor product between a complex line bundle with the trivial bundle is still the complex line bundle itself. So all the 3 conditions will be satisfied, and you will have a formal group by this definition. Moreover, here Txy come from a special choice of the complex orientation. If you make another choice as the complex orientation, you may have some other formal group, but it will always be isomorphic to the original. How to understand the map app geometrically? I guess it's quite hard to give a geometric description of that. So by the tensor product between line bundles, we can show that there must exist such a map with these properties. Yeah, I guess there should be some concrete descriptions about how the map behaves, but I have no idea about it. Sorry. Okay. So finally, I want to give you an example about the commutation of the formal group with the complex K theory. So we consider Ku with the canonical choice of the complex orientation. It is the topological bundle over CP infinity minus the trivial bundle 1. So notice that the topological bundle is also the universal complex line bundle over CP infinity, which is the classifying space BU1. And you know the multiplication on CP infinity represents the tensor product between line bundles. So if you apply the diagonal map, so here this one is the diagonal map, and this multiplication, basically this one classifies a complex line bundle over BU1, which agrees with the tensor product between the 2 copies of the topological bond. So now if you consider the map which defines the formal group, so you know. So if you consider the topological bundle, it will be sent to the tensor product of 2 copies of itself. So here the 3 topological bundles are over the three different copies of CP infinity inside this equation. and you choose the canonical orientation, which is T, X, and Y, to be the tautological bundle minus 1. So you can replace the 3 copies of the tautological bundle by T plus 1, X plus 1, and Y plus 1. So the image of the T plus 1 will be the product between X plus 1 and Y plus 1. In other words, MT will be X plus Y plus XY because M1 must be 1. It is the trivial bundle. In other words, you will have the multiplicative formal group law, which we write as GM on the complex case area K. So finally, let's have a conclusion about the idea of the complex orientation and the formal group laws. So the idea to define the orientation begins with the local orientation, which can always be expressed by either the local homology or the local homology, depending on whether you want to consider the manifold or the vector bundles. Then if you want to choose a global orientation, basically you want to find it from either the global homology of M or the global cohomology of the whole Tom space. Then the E orientation is basically replacing the detecting theory from the ordinary cohomology to the E cohomology. If you want to define an orientation, oh, I guess there's something wrong here. So it should be the complex orientation on E. So the orientation on E is a universal choice of E orientations on all the complex bundles together with some additional compatibility relations. And we know that this can be determined by the choice of the orientations over all the tautological line bundles over CPN, which is further represented by an element in the E cohomology of CP infinity. And moreover, if you further analyze the structure on this cohomology, you can recover something we call a formal group, which encodes the product, which is in fact the co-product if you consider the cohomology theory on CP infinity. So I guess these are all I want to talk about today. In the next talk, Zhipeng will tell you more information about the formal group together with the universal example MU. It is the universal object among all the complex oriented spectrum. Okay, thank you.